Good morning, my name is Fernando Beltran and my partners are Miguel Villamil and Santiago Carvajal. Today we are going to talk about regularization, specifically in linear regression and logistic regression. Firstly, we are going to talk about the problem of overfitting, then we are going to talk about the cost functions, and finally how to implement regularization on linear and logistic regression. So let's start.
Hello, my name is Santiago Carvajal and I'm going to talk you about overfitting. So, to understand what is regularization, we must first be familiarized with the concept of overfitting. So, what is overfitting? By now, you should know some supervised learning algorithms to do regression or classification that work well for many problems. But turns out that when you apply them to certain machine learning application, they can run into a problem called overfitting that can make your algorithm perform very bad. We are going to explain what is overfitting, and then we will be able to study that technique called regularization that will allow us to reduce these overfitting problems and get these learning algorithms to work much better. First, let's see a quick definition from Oxford Dictionaries. So, overfitting is the production of an analysis that corresponds too closely or exactly to a particular set of data and may therefore fail to fit additional data or predict future observations reliable. In order to understand this definition, let's use the example of predicting house prices with linear regression, where we want to predict the price as a function of the size of the house. In this graphic, we have 6 training examples. The first thing that we could do with this data is try to fit a linear function. Doing that, it's possible that we get this straight line fit to the data, but as you can see, this isn't a good model. If we look carefully to the data, we can see that when the size of the house increments, the house pricing starts to increment less, like if it flattened out as we move to the right in the house size. That's why this algorithm does not fit the training data. We call this problem underfitting or high bias algorithm. This means that the model doesn't fit the training data very well. Now, to improve the model, we could fit a quadratic function with this dataset. This is one of the possible results that we can obtain using a quadratic function. As you can see, it works really well. So we could say that this line represents a good model. Now, in the other hand, the other extreme would be if we were to fit, for example, a 4-order polynomial to the data, so the line passes over all the points, as you can see here. For example, here we have 5 parameters, theta 0 through theta 4, and with that we can actually fill a curve that passes through all 6 of our training example. The curve that we get looks like this. This curve seems to do a very good job fitting the training set because it fits all the data training points, as you can see. But this is not a very good curve, so it's going up and down all over the place, and as you can see, that's not a good model for predicting house prices. For example, see the point here. It's saying that with big size you are going to get a lower price. That's not reasonable. So this third situation is what we call overfitting or high variance. And this is the problem that we want to treat with regularization. We will talk about that in a moment. Now, to recap a bit, the problem of overfitting comes when we have too many features. Then, to learn hypothesis might fit the training side very well. So your cost function might actually be very close to zero, or maybe even zero exactly. But you may then end up with a curve like this that is really attached to the training set, and it's not revealing the reality, so that it even fails to generalize to new examples and fails to predict price on a new examples. Here, the term generalize refers to how well a hypothesis applies even to new examples. On this part, we look at overfitting for the case of linear regression. But a similar thing can apply to classification problems. Here, we have a classification example with two features, x1 and x2. One thing we could do is, for example, fit a logistic regression with just a simple hypothesis like this line over here. But if you do that, you end up with a hypothesis trying to use maybe just a straight line like here to separate the positive and the negative examples. And this doesn't look like a very good fit to the hypothesis. So once again, this is an example of underfitting or of the hypothesis having a high bias. In contrast, if you were to add to your features some quadratic terms, then you could get a decision boundary that might look more like this. And that's a pretty good fit to the data, probably one of the best that we can get. As you can see, it separates very well the positive and the negative examples. Finally, at the other extreme, you could fit a very high order polynomial like this, trying to find a decision boundary that fits every training example. This really doesn't look like a very good hypothesis for making prediction. And so, once again, this is an instance of overfitting that probably wouldn't be able to generalize well to new examples. So, now that we know what is overfitting, let's talk about the problem of if we think overfitting is occurring, what can we do to address it? In the examples that we saw, we had one or two dimensional data, so we could just plot the hypothesis and see what was going on and select the appropriate degree polynomial to avoid overfitting. But this is not possible if you have more than 3 features, and usually in machine learning problem you have much more than 3 features, so plotting is not an option. Then, in order to address overfitting, there are two main options for things that we can do: a reduced number of features and regularization. The first option is to try to reduce the number of features. Specifically, one thing we could do is manually look through the list of features and use that to try to decide which are the more important features and which are the features we should keep. Or you can use algorithms for automatically deciding which features to keep and which features to throw out. This idea of reducing the number of features can work well and can reduce overfitting, but the disadvantage is that by throwing away some of the features, it's also throwing away some of the information you have about the problem. This information could be important to your model or to your prediction. So now we have the second option. This second option is the main topic of this presentation. You can use regularization. With regularization, we are going to keep all the features, but we are going to reduce the magnitude or the value of the parameters theta g. Mathematically, you can prove that doing this you can avoid the overfitting problem. This is really good because we could have a lot of features, each of which are useful, so we don't have to throw them away. Now, we'll start to formulate exactly how to apply regularization and exactly what regularization means.